Thank you so much for the introduction. So yes, we're going to start off ambitious and try to understand how neural networks learn features from data. And this, I will say, is a joint work with Misha, who is actually speaking later today, Dima at University of Washington, Daniel and Partha, who were at UCSD at the time of this. And so before I go into feature learning, I just wanted to start off at a high level as to certain observations that are happening in machine learning today. And in fact, I'm going to start with this sort of fundamental machine learning problem, which is how do we actually overcome the curse of dimensionality? And the idea here is, behind the curse of dimensionality, is that typically as the number of features increases, we would need exponentially more samples to build an effective predictor. And maybe just some simple intuition as to why this is. I'm sure many of you are already familiar with this. But the idea is that if I just have one feature, a one-dimensional variable, and I'm predicting a label, then I could just potentially sample densely along this region at some uniform spacing. But if I was to start building a function where I had more features, I would need, if I wanted the same level of discretization, I would start to need exponentially many points in the dimension. And so if D here is like 100 or 1,000, this is going to be an astronomical number of data points. I'm not going to possibly able to do anything here. So how can we possibly overcome the curse of dimensionality? Well, there's certain situations where we can do this, sort of like the multi-index or single-index model setting. And the idea here is that the labels really only, suppose that the labels truly only depend on a low-dimensional subspace of the data. So for example, suppose I have 1,000 features, but really my label is only the product of the first two. So in this case, if I was to somehow discard the other 998 features and just focus on these two, I would really need very few samples to learn this function. And while this is a matter of coordinate selection, this problem is more general. It could be a subspace. In this case, suppose that my label really just depends on the sum of the 1,000 coordinates. This is just a one-dimensional measurement. If I can learn to project onto this vector, then I really only need very, very few samples to solve this problem. Okay. And so if we're able to do even this efficiently, we can overcome the curse of dimensionality. But we've had all these machine learning methods for so long, and what's the problem with them? So just to give an example of a classical machine learning model that suffers from this is something like a kernel machine. And the idea here behind the kernel machine is that I have my data coming in, I have my features, I'm going to apply some fixed feature map and predict a label. And the issue here is that we have to select the feature map, and we a priori don't know what features are necessarily important. And so for example, on the previous slides, how would I possibly know to construct a feature that just subselects a handful of coordinates or projects onto this? So kernels here, the traditional kernels like Gaussian kernel or Laplace kernel or something like this really do suffer from the curse. But on the other hand, neural networks clearly are beating the curse of dimensionality. And so if I take a look at an example like some large language model, something like GPT-4 or Claude, these models are now trained on massive context sizes, massive vocab sizes. In fact, I saw recently there's a challenge on Kaggle for using Gemini 1.5. That thing has 2 million context size, which is seemingly absurd. Yet it still gives good results. So how is this possible? Well, the idea here, the key idea, is that these models are automatically learning low-dimensional representations of the data through training. And this is a procedure that we're going to just refer to in recent years as feature learning. And so the questions that I want to really focus on in terms of feature learning are the following. So how does feature learning actually occur in neural networks beyond just updating the intermediate layer weights? And is feature learning actually just restricted to neural networks, or can we go beyond neural networks and build a general algorithm for learning features? And moreover, how does feature learning actually just result in this sparse low-dimensional structure? And I'll provide some connections to some classical work on this. And so this is going to be the roadmap as our proposed answers to some of these questions. And so the idea here is first we're going to go over our proposed mechanism of how neural networks learn features and data. This is through a mechanism we're calling that's known as the average gradient outer product, or AGOP. We're going to show that you can use the AGOP to actually enable feature learning in general models beyond just neural networks. So you can even take things like kernel machines get them to learn features now as well. And this is through an algorithm we call the Recursive Feature Machine. And then lastly, we're going to show that there is an explicit connection between neural feature learning and well-studied sparse recovery or matrix factorization algorithms. And in fact, that RFM is shedding light on some of the phenomenon that we observe in deep networks today. And this is broadly covering two recent papers. And so I think we've heard a lot about feature learning at the workshop already. But I want to provide a very concrete example as to why updating representations in a network is even useful. Like, it's clear that we're updating weights. Why does this actually lead to better performance? So I'm going to start with a very simple task, just a standard supervised learning problem of I have faces of supposedly celebrities. It's called a celeb A data set, but I've never recognized a celebrity in this data set. And the idea here is that I have these faces, the eyes of the individuals. These are registered images, so the eyes are always in the center of the image. And what I'm going to do is just going to do a 50-50 split. I'm going to take 8,000 examples with glasses, 8,000 without, and I'm just going to train a two hidden layer ReLU fully connected net. And so what am I doing? I'm taking my images, I'm vectorizing them into pixels. There's around 30,000 pixels coming in. I'm just going to predict whether this person is wearing glasses or not. Very straightforward. I can use Atom, gradient descent, whatever you prefer. The neural network is going to get above 90% test accuracy. How do we actually know what features are learned? Why is this a good number? So my claim is that neural networks are actually learning these task-relevant features. How are they doing this? Well, let's take a look at our nonlinear network. We have 3 weight matrices, but importantly, this W1, the first layer, as an example, is just directly multiplying x. So what we can do is we can see that W1 is just scaling, rotating, or reflecting x, and we can just study its uncentered covariance matrix. And because I don't want to keep saying uncentered covariance matrix, I'm going to call it an NFM, a neural feature matrix. This is just W1 transpose W1. What does this thing look like? If we have about 30,000 pixels coming in, this is a 30,000 by 30,000 matrix. And what I'm going to do is a very simple visualization where I just look at the variance terms, effectively, of this matrix, just the diagonal terms. I have one value for every pixel in the image. I'm going to reshape that into an image itself and just visualize it through training. So if I start off, we have a random initialization. There's a certain distribution for this. Essentially, it looks like noise just to the naked eye. But as we continue training, the problem is to identify glasses in images. You'll just see that through training, if you just look at the variance terms, you immediately just pick up a sparse subset of pixels that are just looking for glasses in images, very clearly. Okay.
Well, why is it so discrete in the last drop? Oh,
I think that's just that's just the plotting software for epochs. I think if I actually did SGD or something, it'll be much smoother. So how is this happening? I didn't actually do like L1 regularization, but I'm getting some sparse subset of pixels relevant for prediction. So the big question is, this seems like a very clearly useful representation for this problem. How is it actually happening? And in order to answer this question, let's just take a step back and ask the broader question, which is, suppose we knew nothing about neural nets. If we're just given a predictor f, how would we go about identifying important features for prediction? And the idea here is that I have some input and I have an output. What I can do is I can just perturb each feature. I can just change each feature on the input a little bit, see how the output changes. Those features that most change the output are going to be the ones that are important for prediction. And if I want to do this procedure more generally, instead of just looking at change in output over change in input, which is a derivative or a gradient, I can identify a whole subspace along which the predictor varies, or varies most and varies least by looking at this object, known as the average gradient outer product. And this was studied as early as like 1989 in the statistical literature as a mechanism for feature selection. What does this thing actually look like? Given a function f and some data points x1 to xn, what I'm doing here is I'm taking the gradient of f with respect to the input. There's no parameters here, just with respect to the input of the function. And I'm computing the outer product. So this is just a matrix. Okay, so why is this interesting? Well, our main claim is that neural networks are actually implementing this at every single layer to extract features. And so formally what I'm saying is that these neural feature matrices, these weights transpose weights at each layer, are proportional element-wise to a matrix power of the AGOP computed on the inputs to this layer. And so before I go into details about this, exactly what it means mathematically, why is it important? Why do we care? There's no weights or model here. There's just a function f. So I have a method of extracting features just given any predictor f. So it's just beyond neural networks, and we can decouple feature learning from the selected choice of predictor by just considering AGOP. Okay, so what I'm going to do now is actually just outline evidence for this claim first. So the first portion of this talk is going to be just showing what does the ansatz actually look like for fully connected networks, convolutional nets, transformers, and showing what features do we actually find with the AGOP in all of these cases. Any questions so far? Yeah?
It looks like the empirical feature, right?
What's that?
Empirical feature for the label layers. Looks like you gradient out the product, right?
Yes, yeah.
It looks like the empirical feature.
It looks like the empirical. Yeah, we're going to show that it captures those features. Yes. OK, so just as an example of what this ansatz means for fully connected networks, so here's my diagram of a fully connected network, an L hidden layer fully connected network. If I want to understand what the features of the first layer are, this weights 1 transpose weights 1, I'm claiming that this is AGOP of f with respect to the input data itself, x. And this is to some matrix power alpha 1. If I want to look at the features with respect to the second layer, I'm going to look at AGOP with respect to h1 of x, the inputs to the second layer. And I can do this at any layer, and I have the general formulation here. And this is actually just a claim that we're making, but we have to provide evidence for this. So in fact, I'll return to this theorem later, but the ansatz just holds exactly for deep linear networks when you train them with gradient flow in the limit as initialization goes to 0. And we'll see that the proof is actually not very hard. In fact, I'll have a slide on the proof towards the end.
But what's the intuition for the matrix power?
So I will also provide intuition as to what that matrix power should be later on when I go through the proof. And the intuition is that you can get them to exactly match when the power is.
What is it, 1 over depth?
It's something like 1 over depth, yeah. But it changes for every layer. You have to change the matrix power, for linear at least. In practice, we observe that for empirical, you can kind of pick it to be 1/2, and we have some intuition for this as well from the nonlinear case. Yeah.
So the theorem is for linear case, or?
The theorem is exactly true in the deep linear case, and I'll show why this matters afterwards, because it seems like linear networks may be trivial.
So for nonlinear, it's an approximation.
For nonlinear, it's an approximation. I mean, it's a very good approximation, as I will show shortly. But yes, and we're working on proving this. So that was for fully connected nets. For convolutional nets, how does this work? Well, for convolutional nets, if I'm looking at a layer, the layer is actually just a set of k filters of a certain size, q by q. What I can do to form my weight matrix is I can just vectorize each of these filters, stack them into a matrix of size k by q squared. And now this thing is actually operating on vectorized patches. So the ansatz is going to say that the weights transpose the weights are proportional to the AGOP over image patches, not over the input. And in fact, a similar thing happens for transformers. In transformers, it's a slightly more annoying. We have 3 weight matrices. We have keys, queries, and values. And these are each operating on matrices themselves, but they're really multiplying the columns of these matrices. And so what's happening here is that each of these weights transpose themselves is proportional to an AGOP over just the columns of the input to this. Okay. And so now I've shown you what the ansatz actually states. How does it compare to actual NFMs in practice? So if I take some fully connected networks, here's an example of 5 hidden layer fully connected networks that we trained ourselves on 121 different data sets. If we just look at the AGOP for each layer versus the weights transposes themselves for each layer and compare the correlation, it's extremely high. It's like above 0.9 on the median for every single layer. If we do the same thing, these are models I trained myself, but who trusts me? So we took models from the internet. These are just all of the usual models you're familiar with in classification, ResNets, VGGs with batch norm, and AlexNet. And we did the same thing. So each box plot here is showing you what the correlations between the convolutional feature matrices look like in the AGOP. And we see here that, in fact, for something like ResNet 52, almost all of the convolutional layers are very, very close to 0.9 correlation with the AGOP. Okay?
So you're just treating the matrices as big vectors and computing correlation? Or like...
Yep, exactly. Element-wise, yeah. We treat it as big.
Power in this, or is it going to be 1?
The matrix power here for all of these is 1/2. Yeah, for each layer.
And what are these box plots at, like random initialization?
Great. So I didn't do it for this one, but I have it for VITs, which is what I'll show next. So if you do random initialization for VITs, the average correlation is like 0.17. But after training, you'll see, this is a pretty crazy box plot because this is VIT32L, but you have features for every single head in every single key query value matrix. So you'll have an AGOP for each of those, and we can measure correlation. And that's what it's showing. So the box plots here are per layer across all of the heads in that layer. And in many cases, you see it's slightly lower in some of the later layers for the key weight matrices, but in general, it is still quite high, far higher than what you would get with random initialization. Yeah.
So AGOP itself changes during the training, right?
Yes, exactly.
So how does this comparison
hold through training, or what's the
like? This is at the end of the training. So
this is just for a pre-trained model. Yeah. So this is for a pre-trained model that we just downloaded from PyTorch, and then just.
And AGOP is computed using the trained weights and other layers.
Yes. Yeah. Okay. Yeah.
The AGOP is computed on which data set?
This is all on ImageNet.
ImageNet.
No, full
ImageNet.
resolution ImageNet. Yeah.
I see, full all of it.
So I didn't want to compute AGOP over, average over all the 1 million samples. So this is actually over very few. It's like over 1,000 samples, something like this. Yeah.
And so in this case, when we compute this quantity, like which output of the model that we use, or like this is like correspond to the target level or all the outputs?
So yes, great question. So this is I've presented the AGOP as in terms of gradients for real value. Here you would use Jacobian instead of the gradient. So all outputs.
Yes. The AGOP is computed, is the AGOP of the neural network, not of the data.
Of the neural network, exactly. Yeah. We need a predictor, and then we need it averaged over with respect to a data set.
Yeah. You haven't tried to estimate the one for the actual data.
No, with the true model, yeah, we don't know. But presumably because this thing is getting like 99% accuracy on many things, I assume it's very close to the true AGOP. Yeah.
Is there like a direct relationship between like backpropagation and the gradients that you observe here? Because you make a link between like the values of the parameter matrices and the gradients of your model function.
Yes.
Wondering if there's like a direct connection through backprop in a sense.
So it's not obvious to form that connection because one is gradients of the parameters, the other is gradients of the input to this layer. But I'll show you a case. Like it becomes clear that gradient descent somehow magically does align these two things. Okay. So now I've shown some evidence across these different models. What do the features actually look like? And I guess for those of you who haven't seen this talk, I can make this one slide like very interactive. So let's. Oh yeah, sorry. Yeah.
So the AGOP of the data does not know anything about layers. So,
yeah.
So my question still stands. What is the true AGOP of the data? It's nothing to do with the AGOPs.
Oh, but you need a function, right? I need a function to map from the input to the labels.
Which we have in the data. We have X's and Y's.
There
is an underlying AGOP for that function, but there's nothing to do with the layers. So I mean, that's a very different object.
That's a very different object. So my claim is that the neural net is actually estimating that true AGOP. If you have the AGOP itself.
We have a product of these or something. There are no layers in the real data.
There's no layers in the real data. Exactly. Yes.
But there are also no derivatives of y with respect to x in the real data.
Yeah,
there is a true function, though.
There is a true function.
We're trying to estimate. The estimation is being. I think one needs to distinguish between
the true
function and learning the true AGOP and an AGOP induced by a structure of a learning algorithm, right?
Exactly.
And that's why I was trying to arrive at.
remarkably, I'll show some examples. It seems like no matter, so on certain data sets, no matter what predictor you train, if it achieves good performance, they'll always learn similar AGOPs. So this is somewhat evidence that this is kind of the true AGOP. And there's some very surprising examples coming up. OK, so what I'm going to do is we did glasses classification. Now we can do something like lipstick classification, taking the same data set, just many more samples. So I trained this model. I get 91% accuracy. Now I can ask, like, what are the most important features for predicting lipstick? For those of you who haven't seen this presentation before, any guess? So I thought hair as well. No, it's the eyes. So eyes are the most important thing for predicting lipstick. And you can see this directly by visualizing the diagonal of the AGOP. And in fact, what we can do is really just nail this point and say, if we take all the test images, take the lips of one individual, replace all the lips. I mean, this doesn't even look like a real image at this point, but the model takes almost no hit in test accuracy. It's really like 3%. If I take the smaller subset of pixels for the eyes and I replace all the eyes, you take a 30% hit in accuracy. So the model really in the first layer is just filtering based off of the eyes. And so now we can do the same thing. I mean, this is kind of a cute example, but if I take VGG and I want to understand what are the features given by AGOP at every layer, what we can do is the AGOP now is an operator on image patches. So I can take these test images, take the AGOP for each layer, multiply each patch in my image, and take the norm and visualize it. And if I do this visualization for the first layer, I'll see that I'm doing edge detection. If I go for the third layer, I'll see that it's starting to do some sort of progressive edge detection. And as I go deeper and deeper and look at all of these AGOPs, you'll see that for dogs, it just really focuses on eyes. For things like strawberries and ladybugs, it really focuses on the region of interest for this image. And this just gets amplified. And in transformers, if I'm thinking of edge detection in images, sort of the analog for edge detection in images is, interestingly, happens to be topic modeling or identifying groups of thematically related tokens in text. And so what we did here is we trained our own like GPT-2 architecture transformer on a data set that we had, this tiny stories data set of children's stories. And we just took the AGOP for the value matrices and looked at their eigenvectors and projected the token embeddings onto these. And what you see is that these eigenvectors automatically start to surface specific token groups. So things like food and cooking, adjectives, verbs and actions, and names. And this was an interesting finding. You can just do this with the weights on GPT-2 XL. You'll see that there's certain layers that just focus on like elements like fire, earth, thunder, so on. OK. So this is what I wanted to show in terms of feature learning in neural nets specifically. But for the second portion of the talk, what I'm going to do is I'm going to focus on showing that AGOP can enable feature learning in models beyond just neural networks. And so we stated earlier that AGOP can be computed basically for any function or any differentiable function. And so the idea here for a recursive feature machine, the algorithm that we developed, is that we can just take a predictor that's trained on data and just use the AGOP to select features and iterate. And importantly, if we take things like kernel machines, which have no native feature selection mechanism, we can now enable feature learning in these models just using the AGOP. And so what is the algorithm very explicitly? The algorithm is you give a base learning algorithm for a predictor, whether it's kernel ridge regression or so on. You give me initial filtering matrix, this M0. This is going to be my initial estimate of features. For kernels, we're going to use M0 as the identity matrix. And I have data X and Y. And now what I'm going to do is I'm going to train F on these filtered samples where I multiply each of them by M at time t, and I just predict the labels Y. And the second step is going to be I'm going to update my M as the AGOP of my current predictor over the existing data set to some matrix power alpha. And I will show how varying alpha changes what happens in this process later towards the end of the talk. And we're just going to iterate the following procedure. And so what I'm going to show now is that RFM actually enables feature learning with kernel machines. This is just an example to show what kind of features just any general model learns. Any questions on the algorithm? OK. So we did all these examples of glasses and faces and things like this. So we can just start with that and say, we knew the neural network was sort of picking up on this region of glasses if I looked at the diagonal of the AGOP or the weights transpose themselves. Now what I can do is I can train a kernel machine with the Laplace kernel, just solve kernel ridgeless regression in this case, and now take the AGOP. And if I do this and I compare, you'll see that the neural net and the kernel both identify almost exactly the same features, just in terms of coordinate selection. And if I, instead of looking at the diagonal of these matrices, I look at the top eigenvector, you'll see that you get like some direction of faces with just the glasses. As a fun example, and I think I messaged Misha about this like at 10 a.m. at night when I first found it because it was so horrifying. If you try to see what features are important for smiling, you'll see that all models give you this kind of like clown face. And if you look at the top eigenvector, you'll see that it's just like a prototypical picture of someone being happy. And so what's interesting is that, I mean, this is the interesting point you brought up. These are two completely different models, yet you train them on the data set, you look at the AGOP, it's almost exactly the same features. For the first layer, yes.
But what's between the left and right pairs?
The left is the diagonal of the AGOP for these models. The right is the top eigenvector, just reshaped into an image. And in practice, just to show how important feature learning is we took this UCI data set of 120 data sets. They're tabular data. We just did the straightforward thing of take kernels, use the AGOP to enable features, and see how much of an improvement you get. And it turns out that over the 180 baseline models that were trained on this data, RFM with the Laplace kernel and AGOP actually did the best. And if we just compare Laplace kernel without feature learning to Laplace kernel with feature learning, in almost every case, we see that feature learning gives you some boost. And in certain data sets, there's like up to a 20% boost in accuracy just by doing feature learning. Okay. So this is all for tabular data. And so what I wanted to show next is how it works for image data when I talk about learning features on patches. And I'm going to start with this very synthetic example. And here what I'm going to compare is features learned by just a one hidden layer convolutional network on a toy data set versus features learned by AGOP of a convolutional kernel. And the way to think about a convolutional kernel here is I'll just chunk my image into patches, compute the kernel between patches of images, and just average. And so the data set I'm using here is very synthetic, but will illustrate the point of how feature learning is beneficial. So my class 0 images are just pure random noise. Class 1 is just you have a little star signal in a random position in the image. And so if I train either of these models and I look at the eigenvectors of the AGOP, what you'll see is it's just exactly the top eigenvector as an image is looking for the color yellow. Every eigenvector afterwards is looking for contrast between yellow and its negative, which is blue. And in fact, if I reintroduce these features, even though the convolutional NTK got around like 80% on this task, the convnet is basically perfect. And now if you introduce this feature, you'll see that ConvRFM is also just pretty much perfect on this data set. So why is this happening? If I was to do the exact visualization of how this matrix transforms the features, what I'm doing here is I take an image, I'm chunking it into all 11 by 11 patches, and I've stitched them all together for you here. And what I'm doing is I'm taking each patch, multiplying it by this matrix that's looking for the color yellow. This just immediately kills all the noise, amplifies the color yellow. And when I fold this back down, what you'll see is that you've just killed off all the noise in your image and then highlighted the star. And this is translation equivariant because it's an operator on patches. So no matter where my star is in my image, it will just amplify the star. If I have just pure random noise, it just slightly amplifies the colors yellow and blue. And so here you can see that there is a benefit to doing just AGOP on the patch level. This is a synthetic task. We can ask now what happens when you do AGOP for a convolutional kernel on a real data set. And so what I did here is just, again, took a very synthetic data set of, a very simple data set of street view house numbers. And the idea here is we have 70,000 training examples where the goal is to just predict the center digit in an image of a house number. when you look at the eigenvectors of the AGOP of a convolutional kernel, you'll see that the top two eigenvectors are almost always just horizontal and vertical edge detection, which is exactly what we found in convolutional nets. Now you're doing it for a completely separate model. With the AGOP, you find exactly the same features. These features are just universal edge detectors. If I take an image from ImageNet, apply the AGOP to this, it'll just highlight all the edges in the image. And so I also find it, even though it's just like first layer feature learning, it is quite surprising that on a realistic image classification task, the features that the model learns that are useful are exactly just edge detectors. Yeah.
Wait, so could you get the same thing out of these features, not by like doing the whole propagate forwards to find F and then backwards to find the AGOP, but just like kind of convolving against these like local filters? Like, do you need the whole AGOP rigmarole, or can you just use these filters to get this like edge detection?
Oh, you just use the filters, right, to get edge detection. But I'm learning the filters from the AGOP. Like these are the eigenvectors of the AGOP.
Oh, okay.
Yeah.
You already answered the question.
How's the behavior of adversarial images?
This is something we haven't investigated. The only adversarial example I had looked at was like for those faces with the. You can see that perturbing like some small subset of pixels will change the output, but I don't know what the features will look like here. Okay. So in the last portion of the talk, what I'm going to show is that the theory that we've built up so far with just AGOP and RFM actually sheds light on the connection between feature learning low-rank representations of data and classical algorithms for sparse recovery. And so to start off this section, I want to start off with an interesting phenomenon arising in deep linear networks that was actually written about when I first started my PhD. In fact, this was like one of the first few series of papers I read when I started. And the motivating problem we're going to look at is just low-rank matrix completion. And so the idea here is that I'm given some matrix Y, where I have some subset of observations, but it's corrupted, so I'm missing some observations in this matrix. And the goal here is we just want to reconstruct these missing entries in a way that gives me a low-rank reconstruction of Y. Why is this problem interesting? It turns out that this idea of low-rank reconstructions is exactly what's useful for capturing the intuition for movie recommendation systems. And low-rank matrix completion matrix completion itself was a challenge posed by Netflix, where you had ratings for different movies given by users. You have some missing observations, and the goal is to fill in the missing entries. Low-rank reconstructions capture the intuition that users who rated movies similarly in the past should rate movies similarly in the future, or things that they haven't seen. And so the experiment I wanted to start off here with neural nets is what happens when you start using deep linear networks for matrix completion. And so if I start off with the simplest case, I just have one weight matrix. It's a one-layer linear network. I just have a matrix A, and my goal is to just reconstruct the observed entries by updating A. So I can train A using gradient descent, and this is pretty straightforward to see. If I start with A at 0, the entries of A for the missing components corresponding to the question marks never get updated. And so my reconstruction just looks like this. It's just I perfectly fit all my ones. I put zeros everywhere else. And so this is useless. I don't want to just put zeros everywhere. Instead, what I can do is I can use deep learning and just go deeper. And instead of using one layer, I use 2 layers. And here, interestingly, what was found is that you get to pick a width for this first layer. If the width is larger than the input, even if the width is larger than the input, if you train both of these matrices using gradient descent, surprisingly what you find is that the reconstruction is more biased towards the low rank reconstruction for the data. And in fact, if you keep increasing depth, you'll start to see that it's biased more and more towards low rank. And there's some drop off after like 3 layers or 4 layers or something. And this is a phenomenon that was identified, many years ago. There's work by Jason Lee in this area. But these were the papers I had read at the time that focused. The first paper focused on the 2-layer case and understanding the implicit bias of overparameterized networks for matrix factorization. The second one extended it to the deep linear network case. And so the question is, we've developed all of this theory for AGOP and RFM, how does any of this apply? Can we use this theory to actually recover the existing behavior we see with neural nets? And so what I want to start with is just a proof that the ansatz that we have holds in this setting. And how does the proof go? Well, let's just, instead of focusing on the matrix factorization case, let's just focus on something like linear regression. I have some input x. I have a predictor. It's a 2-layer linear network A times B. What I can do is I can take the gradient of f. This takes the value B transpose A transpose. This is a constant for any x. If I look at the AGOP, this is just B transpose AB. This is going to be my first equation. On the other hand, in these papers that had studied this phenomenon, there's an interesting conservation equation that holds when training these models using gradient flow, and this is known as balanceness. And the idea here is that if you use gradient flow, which is continuous time gradient descent, and you take the limit as initialization goes to 0, you have just A transpose A as B transpose through the training process. So now it's pretty straightforward to put 1 and 2 together. I just take the AGOP. I have the term A transpose A in the middle there. I'm going to substitute equation 2, and you just immediately see that AGOP of f is just B transpose B squared. And this is the ansatz. So we said AGOP of f to the power 1/2 is exactly just B transpose B through training. And this proof extends straightforwardly to the deep linear case. So now we know that the ansatz actually holds in this case. And so this should provide further evidence that whatever phenomenon we're observing in deep linear networks, we should ideally be able to recover purely through the AGOP. Okay. Any questions on the proof? Okay. And so how does the algorithm for RFM work in this case? Well, we have a matrix Y with some potentially missing observations. We have an initial weight matrix B, which I start at the identity. And now instead of using gradient descent to update A and B, what I'm going to do is the following procedure. I'm going to take my model, which is A times B. I'm going to fix B, solve for A using least squares. And so this model will interpolate the data for all the observations. This is my training the predictor step. What I'm going to do for the second step is just basically use the AGOP update that we had on the previous slide. So I'm going to show that B, just update it as B transpose AB to some power alpha. And we saw that alpha was something like, what, 1/2 or actually for 1/4 for the 2-layer linear network. But here I'm going to vary the value alpha. And I'm just going to repeat these steps over and over again. So this is my proposed method for, instead of training a 2-layer network with backpropagation, I'm going to train it in this way. Any questions? Okay. So how does this work on the example that we saw here? So instead of setting alpha to be 1/2 or something like this, let's just start with alpha of 1. So I started with B at the identity. I'm solving for A. I'm solving least squares. This is the same thing as training just a 1-layer linear network. It just puts zeros everywhere. So it's completely useless at 1 iteration. If I do 2 iterations, you'll see that it immediately goes to around 0.45, 0.45. If I keep going for 100 iterations, you just numerically get 1. And this is an example that I just ran like a few nights ago. So you'll see that it just exactly recovers the rank 1 reconstruction in this case. So this model is exhibiting the same phenomenon as deep linear networks, but this model is seemingly very tractable to analyze. Why is this happening? How does RFM actually recover this low rank matrix in this case? It turns out that RFM, as we've written it, is exactly a reparametrized version of a known algorithm for matrix factorization called iteratively reweighted least squares. And this was used as early as 1961. But for matrix factorization was really prominently used by these 2 papers in 2011 and 2012. And so what we can do is, since we have these dynamics, we can actually just understand what the first order critical points are, and we can understand what the fixed points of RFM are. And in fact, if we looked at the fixed points of RFM, it turns out those are critical points of sparsity or low rank encouraging objectives. And in particular, what we have here is instead of solving least squares and fitting the data, you're now implicitly minimizing a specific norm or pseudonorm while fitting the data. And just to give some examples of what the theorem looks like, for different values of alpha, if alpha is 1/4, this actually just corresponds to the case of two-layer linear nets. You get exactly nuclear norm minimization. If alpha goes to 1/2, interestingly, this corresponds to the implicit bias of infinitely deep linear nets. You get the log determinant penalty on the singular values of your reconstruction. If you go even larger, you get something that you can't recover from implicit bias of deep linear nets, but it ends up being something that's quite useful for low-rank reconstructions, and it's this negative power penalty. So the signs in the theorem actually switch so that you get the right curvature for inducing sparsity. And it's just very obvious from the pictures. If you can actually minimize this objective, you're going to get a much, much sparser solution. Okay. Any questions on this part so far? So the nice part about this is that we had this power alpha, this matrix power that we've had through the talk. We can just tune this thing and control the amount of sparsity that we want in our model. And it turns out in some synthetic examples, in some simulations, we just took 200 by 200 matrices, and we asked if we just IID drop out samples, what's the fewest number of observations we need with these different algorithms to reconstruct the true low-rank matrix up to 10 to the -3 mean squared error. And what we find is that linear RFM does incredibly well, far better in terms of sample complexity under this measure than nuclear norm. And in fact, deep linear networks like depth 3 also outperforms the nuclear norm, but linear RFM does quite a bit better in these cases. And if I actually just zoom in to one of these plots just to show what the simulation looks like, let's say I look at a synthetic 200 by 200 matrix that's rank 15. If I start randomly sampling observations from this matrix and reconstructing, we'll see that linear RFM actually does quite well with few samples. Interestingly, deep networks, what ends up happening is they underestimate the rank, and they take a massive error when you have very few samples. As you get to a certain regime, deep networks all of a sudden estimate the correct rank and start doing well, but linear RFM just generally does quite well on this task, and also far better than nuclear norm. Okay. Any questions on the experiment?
Sorry, quick question. I missed when in the comparison with the deep neural networks, the loss is what?
So the loss that we're training to is the test loss to the true synthetic matrix that I created. Yeah, and I want that to be less than. Yeah.
Quick question.
Yeah.
What does train MSC look like on this? Do you have a gap? Like grokking, for example, would have maybe the.
Oh, so train MSC, like we're able to interpolate the data in all cases. So train MSC would be basically.
I see. So okay, but this is not a training curve, right? This is at the end of training.
Yes.
Okay, sorry, yes.
So maybe this is some type of grokking, actually. It's just drop on the blue line.
Yeah, very possible. I mean, this is something that you consistently see with deep neural networks on many different matrix completion tasks. And that's a nice segue into Misha's talk later, which will be also about grokking with RFMs. So, okay. So with that, I wanted to conclude the talk and say that we started with this ambitious, motivating problem of understanding how deep neural networks learn features from data, and this has been a very fruitful question for us. Some key takeaways, like I think that it's clear, it's becoming clear at least, that AGOP is a key mechanism for understanding feature learning in general machine learning models, just beyond neural networks. And also that RFM in certain cases is just a nice, analytically tractable model for understanding various deep learning phenomena, and Misha will give another example today. And being part of the Broad Institute at MIT, a lot of my work is also on using machine learning for scientific applications. We're actually finding that RFM is quite useful in terms of its interpretability for many biological applications. And so I feel it's like a quite nice tool to understand, features and make discoveries in these settings. And maybe one quick resource I wanted to share is just a link to software. we've packaged RFM in a very simple way, and there's like a Jupyter Notebook tutorial for this. You can just, given a model, this fit function will just fit a Laplace kernel and take its AGOP, and you can control the number of iterations, regularization, a number of things. And M is just the feature matrix, so you can get the feature matrix through training. Okay, and maybe before I conclude, because I work on machine learning for scientific applications, I was asked by my advisor to share that we have an ongoing challenge for those of you who are interested in this area. Our center is actually hosting a challenge for making discoveries for autoimmune diseases, in particular identifying genes for a specific type of disease known as inflammatory bowel disease, or IBD. And so for those of you who are interested, feel free to sign up and register. It's open participation. There's prizes. And let me know if you have any questions. I should also mention Boris has been very involved with Foundry, and they're providing some compute for this. I don't know if I should have said that. Yeah. Okay, so that's the end of my slide.